How's it going, everybody? And today I'm going to be looking at machine learning. Garon's book. I'm currently trying to become a data analyst. And this is probably one of, if not the best read on machine learning. It goes through so much. So making sure that through the data, the plane going over by, so don't worry about it. So what we have here in Garon's book is a project, and what he's using is a data project from California. What you need to keep in mind is what Garon is telling, and that you are basically a consultant in a sense. You're going to have your company or a company hire you. They're going to give you some data. You're going to clean the data, and then they're going to say, "I want to know this question from that data." And you, as a data analyst, have to be able to assess what models to use, how to clean it. Is the data that they've given you and that you have good enough to answer the question? So let's see here. So here we have pipelines. I've already read that one. Okay. Notation. I've read a lot of this in a previous stream. So if you want to go and check that out. Okay. Our environment. You can just install Jupyter via Anaconda 3 kernel. Oh, going it's around. Data would be available, additional data, and spread across multiple documents and files. To access it, you would first need to get your credentials and access authorization and familiarize yourself. Just download a CSV, and you could use your web browser to download it. Okay, and then what you're going to do is we're going to import this element, which is the download route from GitHub, and we have our path, which is the data set, and then we have our housing. Now, when you call directory in your workspace downloading, and here you have it. Now let's load the data into Pandas. Again, Pandas is a library that allows you to have data frames and structure and manipulate data frames and structures. Okay, this function returns a Pandas data frame, object containing all the data. Let's look at the top 5 first rows. So this is the equivalent of having housing.head is the equivalent of looking at the top first rows of your Excel sheet. Each row represents one district. There are 10 attributes. You can see the first 6 in the screenshot. Longitude, latitude, Haussian median, total rooms, total bedrooms, population, households, medium income, medium house value, and ocean proximity. The info bracket method is useful to get a quick description of the data, in particular, the total number of rows and each attribute's type and number of non-null values. Okay. And then we have housing info. There are 20,640 instances in the data set, which means that it's fairly small by machine learning standards, but it's perfect to get started. Notice that the total bedrooms attribute has only 20,000 non-null values, meaning that 207 districts are missing this feature. We will need to take care of this later. All attributes are numerical, except the ocean proximity field. Its type is object, so it could hold any kind of Python object. But since you loaded this data file, you know that it must be a text attribute. When you looked at the top 5 rows, you probably noticed that the values in the ocean proximity column were repetitive, which means that it is probably a categorical attribute. You can find out the categories exist and how many districts belong to each category by using values. Let's look at other fields. So at the moment, what Giron is doing is just trying to understand what's in the data. Data preparation, exploratory data analysis. What am I dealing with here? What is my data types? Here we have our 6 columns, which is what he's calling an attribute. And then we're looking at the data described, and here what you have is your standard deviation for longitude, standard deviation for latitude, standard deviation for housing median, minimum, your means. So this is really important. Another quick way to get a feel of the type of data you're dealing with is to plot a histogram for each attribute. A histogram shows the number of instances on the vertical axis that a given range you can plot. Okay, so here's your histogram. Good. So then what we can do is we can start to begin to see how the pattern of the data and the spread of the data within each field. So the first median income attribute does not look like it expressed in USD. After checking with the team that collected the data, you are told that the data has been scaled and capped at 15. At 15, actually. 15,000, I think. For higher median income at 0.5, the lower median incomes, the number represents roughly $10,000. Actually means about $30,000. Working with processed materials is common in machine learning. Okay, the housing median age and median house values are also capped. The latter may be a serious problem since it is your target attribute. Your machine learning algorithms may learn that prices never go beyond that limit. You need to check with your client's team to see if this is a problem. If they tell you they need precise predictions, even beyond 500,000, you may only have 2 options. Collect more proper labels for districts, remove those districts from the training set. So again, you have to be aware of how the data is coming to you. As you said, that might have a big impact. These attributes have very different scales. We will discuss this chapter before feature scaling. Finally, many histograms are tail heavy. They extend much further than the right of the median to the left. This may make it a bit harder for them. Some machine learning algorithms to detect patterns. We will try to transform these attributes later on to have a better shaped distributions. Here he's saying they're going further. The spread is very big, and they're or actually not. The spread is very big. In some of them, they're not normally distributed. I don't know. This will be the closest to a normal distribution. There's a big skewed element in this data set. You have to learn all of this statistic language, which is what I'm doing at the moment. Even I need to look over how I understand my histograms. Okay, so we create a test. This may sound strange to voluntarily set aside a part of this data. After all, you have only taken a quick glance at the data, and surely you should learn a whole lot more about it before you decide what algorithms to use, right? This is true. But your brain is an amazing pattern detection system, which means that it is highly prone to overfitting. If you look at the test, you may stumble upon some seemingly interesting pattern in the data that leads you to select a particular kind of machine learning model. When you estimate the generalization error, your estimate will be too optimistic and you will launch a system that will not perform as well as expected. This is called the data snooping bias. Now, this idea of creating a test is very, very, very interesting. You're splitting your data up, as he will show us. So here you bring in your code. a function like this. Train. So then what we're doing is creating a definition or function. And then we're bringing in split train test data, shuffled indices. So we're shuffling the data, and then we're test set size. The length of the data multiply the test ratio, test indices shuffled, train indices shuffled, and then we're going to have train set, test set equals split train test housing. Okay. And we're splitting, we're taking a part of our data away. How can I put it like this? It's like when you get tested in a maths test. These are, but they're not part of what you're going to be trained on as a young kid. You know, if you go to any exam, you're not getting all the exact same questions. You're getting them similar, but they're based on the same curriculum. And this is the exact same thing that a machine learning algorithm needs to go through. Well, this works, but it is not perfect. If you run the program again, it will generate a different set. Over time, you or your machine learning algorithm will get to see the whole data, which is what you want to avoid. The solution is to save the test set on the first run and subsequent runs. Another option is to set the random number generator seed before calling random permutation so that it always generates the same. These solutions will break next time you fetch and upload a dataset. A common solution is to use each instance's identifier to decide whether or not it should go in the test. For example, you could compute a hash of each and put that instance in the test set. The test set will remain consistent across multiple runs, even if you refresh the data. The new test set will contain 20% of the new instances, but it will not contain that will be in the training set. Here, so you're trying to keep. So it will generate a different data set. Okay. And you don't want that. You want to keep your data set. So one solution is to save the test set on the first run and then load it in subsequent. Another one is to set a random generator seed. And this is what they're doing here. Okay. Unfortunately, the housing data that does not have an identifier column. The simplest solution is to use row index as the item. If you use the row index as a unique identifier, you need to make sure that the new data gets appended to the end of the data set. If this is not possible, then you can try to use the most stable features to build a unique identifier. For example, a district's latitude or longitude are guaranteed to be stable for a few million years. So you would combine them into an ID like so. So he's constantly problem solving at the same time. Scikit-learn provides new functions. And another thing to keep in mind, as I'm going to be reading this over and over again, is why is he doing what he's doing? That's the fundamental key, you know? And he'll help us as he goes along in the book. Scikit-learn provides new functions to split data sets into multiple subsets in various ways. The simplest function is train test split, which does pretty much the same thing as the function as split train test defined earlier, with a couple of additional features. First, there is a random state parameter that allows you to set the random seed generator seed as explained previously. The second, you can pass multiple data sets with an identical number rows, and it splits them all the same. This is very, very useful, for example, if you have to separate data frames from labels. So far, we have considered purely random sampling methods. This is generally fine if your data set is large enough, especially relative to numbers of attributes. But if it is not, you run the risk of introducing a significant sampling bias. When a survey company decides to call 1,000 people to ask them a few questions, they don't just pick 1,000 people randomly in a phone book. They try to ensure that these people are representative of the whole population. For example, the US population is composed of 51.3% female and 48.7% male. So a well conducted survey in the US would try to maintain this ratio in the sample 513 female and 487 male. This is called stratified sampling. The population is divided into homogeneous subgroups called strata, and the right number of instances is sampled from each substratum to guarantee that the test set is representative of the overall population. If they used purely random sampling, there would be about 12% chance of sampling a skewed test set with either less than 49% female or more than 54% female. Either way, the survey results would be fairly significantly biased. Suppose you chatted with experts who told you that the median income is a very important attribute to predict median housing prices. You may want to ensure that the test set is representative of the various categories of incomes in the whole data set. Since the median income is a continuous numerical attribute, you first need to create a basic income category attribute. To create an income category attribute by categories. Category 1 ranges from 0 to 1.5, category 2 from 1.5 to 3, and so on. So here we have this idea of bringing in train set, test set. And what I'm going to do is I'm going to leave it there. Till next time. How are you getting on? Not. No, you're not.